Hi everyone, welcome to lesson 2, which is bonding in compounds. We're going to have a wee look at the polarity of bonds. So we're going to explore examples of different compounds to learn about polarity. What does it mean? What do we have to know about it, etc. Our success criteria are identify the type of bond in any compound given. So we're going to do some questions at the end of this, which are in your pupil booklet, and hopefully be able to answer all of these correctly at the end. So, the polarity of bonds. We're starting on page 3 of the pupil booklet. So, what has polarity to do with? It has to do with the difference in electronegativity between the atoms. So, if we take a molecule of hydrogen as an example, we know that hydrogen bonds as H2, in other words, covalently bonded one hydrogen to the other via the sharing of the electron. If you go to page 11 of your data booklet, the first thing you want to do is find the atom in the compound that you are interested in. So if we have hydrogen bonded to hydrogen, we are looking for hydrogen, which is conveniently right at the top. So once we've found hydrogen, we are interested in the electronegativity, which is the very right-hand side, and we can see that hydrogen's electronegativity is 2.2. So what does this mean now? This diagram is also in your booklet. If the atoms have the same electronegativity, so in other words, this can be when you have two of the same atom, for example, like the diatomic elements, hydrogen is an example of one of those, or there are some other elements that have the same electronegativity even though they are not the exact same element. But what this means is that both of these atoms are sharing the electrons, we would say, evenly. They both have the same attraction for the bonding electrons. If there is no difference in the electronegativity, then the bond is said to be a pure covalent bond or a non-polar covalent bond. It doesn't matter which of these you say, both of them will get you the mark. Personally, I like to call it a pure covalent bond because in my mind it just reminds me it's pure, there's no difference in electronegativity or very small difference in electronegativity, and that helps me remember. So, no difference in electronegativity, you have a pure covalent bond or a non-polar covalent bond. In the opposite scenario, where the atoms have a difference in electronegativity that's more than 0.4, so even though in the last example we had exactly the same electronegativity difference, there was no, in other words, no difference, you can have a non-polar bond or a pure bond, covalent bond, where the electronegativity is 0.1, 0.2, 0.3, or 0.4. Those are all fitting into the category of pure covalent or non-polar covalent bonds. The opposite to that scenario is where you have a difference in electronegativity that is greater than 0.4, which means the electrons are being pulled to one atom. So we already know a bit about electronegativity. It's how well the element or the atoms of that element can hog electrons, I like to say, or take electrons over to their side. So the electrons are being pulled to one of the atoms more strongly than the other. I'm going to have to move my little box here. So in this situation, we have hydrogen, which we already noted has an electronegativity of 2.2. If we look on page 11 of the data booklet, we'll find that chlorine's electronegativity is 3. Now, looking at those, that is a difference of 0.8. That's quite a large difference, greater than 0.4. So where there is a difference greater than 0.4, the bond is said to be a polar covalent bond. This stuff that we are talking about right now is on page 3, kind of towards the bottom of page 3 of your notes. You do have blanks here to fill in. So what does this mean? This means that the electrons are being shared unequally, and it creates something called a dipole in the bond, where one atom is slightly positive and the other is slightly negative. Now, what this means is the electrons are more likely to be found with the more electronegative element. In this situation, it's chlorine, which means that it's going to have a slight negative charge. Because those electrons are so close to that atom, it's going to have a slight negative, and that is this little symbol here. It's called delta, and delta just means slightly. So this part of the scenario is slightly negatively charged, which means if hydrogen has kind of not lost electrons completely, but is having them pulled away from hydrogen towards the chlorine, it's going to be in a deficit of electrons. So it's going to have a slightly positive charge. So on the chlorine side, the electrons are in excess. On the hydrogen side, they're in a deficit. So that results in this little partial charge here, which is a positive on the hydrogen side and a negative on the chlorine side. Now, this situation where you have a bond and you have a slightly negative part and a slightly positive part is called a dipole. So dipole, let's break that down. Di means two, and poles, like north and south pole in a magnet, are different charges. So dipole is the two different charges, the slightly negative charge and the slightly positive charge. That is what that means. Let me move myself again. So, at the top of page 3 then, you have this bonding continuum. And that tells you how likely a bond is to be non-polar, remember that's pure, polar covalent, or you also have ionic. And it's based on the differences in electronegativity. So if we have a look at this then, you have non-polar covalent or pure covalent with the lowest difference in electronegativity. So that's from 0 to 0.4 of a difference in electronegativity. Next up, a wee bit higher, we have polar covalent, where there is a difference from 0.5 to 2. Anything higher than 2 is not going to be a covalent bond, and it's because the electronegativity difference is so strong that in this example here between sodium and chlorine, the chlorine will completely remove an electron from sodium, as you know. That's how an ionic bond is formed. It has the largest difference because that electron is completely removed. Chlorine is so much more electronegative than sodium that sodium doesn't even hold on to the electrons even a little bit. It just completely lets them go, which we already know through ionic bonding knowledge. So, hopefully that is enough information for you to fill in the blanks in your booklet. Remember, covalent bonds can be two new things: non-polar covalent or pure covalent and polar covalent. So if you were asked to kind of show your knowledge of this, or any questions to do with the polarities or anything like that, then I would always start by drawing whatever you're being asked about. So here is a bond between carbon and chlorine. What you would then do is go and look up the electronegativities. Those are at the bottom. So carbon has an electronegativity of 2.5, chlorine has an electronegativity of 3. Now, because there is a difference of 0.5 between those two atoms, then we know that this is a polar covalent bond. Now, because it's polar covalent, because we have this difference and it's greater than 0.5, then that means that chlorine is hogging these electrons more than carbon is. So we are able to put in our partial charges. The delta negative goes with the chlorine because it is more electronegative. It will take the electrons towards itself. And carbon is going to then have an electron deficit. So it's going to be positively charged partially. Now, don't label the partial charges as dipoles. That's not the dipole. The dipole is the whole thing. So the dipole is created where you have some negative charge and positive charge, as in the two poles. The individual charges themselves can just be labelled as partial charges. So if we flip over to page 4, you'll see that we can have a look at this table here. The C to Cl bond has a difference of 0.5, so it's going to be a polar covalent bond. The phosphorus and hydrogen has no difference, so it would be called a pure covalent bond or a non-polar covalent bond. And O to H, so oxygen to hydrogen, has a difference of 1.3, so again, it is more polar than the carbon to Cl bond, but it's not enough of a difference to be ionic. Remember, we're looking for something with a difference greater than 2 for it to be ionic. If, however, we were asked to put these in an order of increasing polarity, then we would start with the lowest difference, then the next highest difference, and then the highest difference in electronegativity. So it's all about the difference in electronegativity. That is what we're always looking for. So we wanted to be able to identify the type of bond in any compound given. Let's work through some of our questions, and hopefully if we get all the answers correct, we can say that we have achieved our success criteria for this lesson. So, just like Mrs. Calder does, I am going to show you the questions. Here they are here. Now, please note that question 2 is a little bit different in your booklet. It will be state the bonding pure covalent or polar covalent or ionic present in the following compounds, rather than just covalent or ionic. So pause the video just now, have a go at these questions, write them down in your jotter or a bit of paper, and then unpause the video and check your answers. Okay, so first one, complete a table as above to show the electronegativity and the differences for the following bonds. So very, very straightforward first question. We are going to look up each of these elements in turn, find out their electronegativities, and then look at the difference. So carbon has an electronegativity on page 11 of 2.5. Nitrogen has an electronegativity of 3. Therefore, the difference between those two is 0.5. Carbon again is 2.5. Oxygen is 3.5. So that means we have a difference of 1 this time. And phosphorus and fluorine, phosphorus is 2.2. Fluorine is 4. That gives us a difference of 1.8. So this is just a question to make sure that you can use your data booklet, find the electronegativities, and work out the differences between the elements. Question 2. So state the bonding, either non-polar, polar, or ionic, for the following compounds. Hydrogen bromide, first of all. So like I said before, I would draw the symbols first. So hydrogen, line, Br. I would then look up the electronegativities of the atoms. So hydrogen is 2.2 and bromine is 2.8. That is a difference of 0.6. That's over 0.5. So we're going to have to add the partial charges in because we have a polar covalent bond. Sodium chloride is next. Again, let's draw the symbol. So we have an Na bonded to a Cl. The Na, sodium's electronegativity is 0.9. Chlorine's is 3. So we have enough of a difference here, a 2.1 difference, that warrants an ionic bond. So not a covalent this time. We're over 2.0 in electronegativity difference, which means the chlorine just takes the electron. It doesn't even ask sodium if it wants to share, it just takes it. C, we have carbon tetraiodide. So when you have something like this, it's important to remember we are talking about the bonding present within the compound. So even though we have carbon tetraiodide, we are still just looking at the bond between carbon and iodine. Now, carbon has an electronegativity of 2.5. Iodine has an electronegativity of 2.6, which means we have a difference of 0.1. Now, that difference puts us in the category of a pure covalent bond or a non-polar covalent bond. Either of those is fine. Next one is state the bonding and structure in A, phosphorus, and B, carbon. Now, phosphorus is one of our covalent molecular solids. We just have to remember that. Remember, it's your P4 molecules, and they exist as solids at room temperature. Carbon, you will think straight off the bat, network, covalent network, as in diamond or graphite. But remember, carbon can exist as a covalent molecule as well, a solid in the form of a fullerene. But most people will go for covalent network, which is absolutely fine, as long as you specify that it's diamond or graphite you're talking about. Next, towards which element do the electrons lie in a molecule of hydrogen fluoride? So again, this is the exact same process every time we do one of these questions. We're going to write down what that bond looks like. So we're going to have a hydrogen line to a fluorine atom. We're then going to look at the electronegativity of each in turn, and then look at the difference, and it will tell us which kind of bonding we are looking at here. So we've got hydrogen fluorine here, as I've drawn. Hydrogen's electronegativity is 2.2 and fluorine's is 4. So that is a difference of 1.8. Therefore, we have to add in our charges like I've done. So delta negative goes to the fluorine. It is more electronegative, so it will pull the electrons closer to itself. Hydrogen has that electron deficit. They are kind of further away from hydrogen, so it's slightly positively charged. And what kind of bonding is this? It's called polar covalent bonding. The question doesn't specifically ask for that, but it's just good to familiarise yourself with these. So the answer to that question is the electrons lie towards the fluorine. And that delta negative answers the question for you. Or you can add in a little bit that says the partial negative charge tells us the electrons are being pulled more strongly towards fluorine. And that is it. Hopefully, you will, after that lesson, know that there are 3 types of bonding now. You have covalent being split into 2 different parts. If the electronegativity difference is below 0.5, so 0.1 or 0 to 0.4, then you have what's called a pure covalent bond or a non-polar covalent bond. That's the first section. The second section of covalent bonding is if the electronegativity is 0.5 to 1.9. That means you have a polar covalent bond. Now, when you have a polar covalent bond, you should always write in the partial charges. That lets the marker know that you know towards which element the electrons lie. Lastly, if the difference is 2 or greater, that takes us into the ionic bonding territory. We're no longer sharing electrons. The electronegativity difference is so great that the atoms are actually taking them without asking, really. Not sharing at all, just taking them. If you have any questions, then pop a question on the Google Classroom and myself or Mrs. Calder will get back to you. Thank you very much for watching and have a great day.